All right. Hi, good morning, everyone. Thanks for coming. We are going to let folks join, so we'll be another minute or so. My name's Melissa Orkin. I'm here with Becky Lord. We're really honored to have you here this morning for our Secrets to Teaching Math Facts webinar. So this is going to be an amazing hour. I know as educators, the last few weeks of the summer are very precious. So we really are honored that you're here today. I have my fan going in the background, so I'm just going to go actually and turn that off. Pardon me.
I'm actually going to do the same and turn my air conditioning off. For noise.
A lot of white noise happening. Good morning. Hi, everyone. Thanks for joining us. We are going to get started in just a minute. My name is Melissa Orkin. I'm here with Becky Lord. If you want to grab a piece of paper to take notes, I bet you're going to have information that you're going to want to look back on that Becky's going to share. I'm also going to go ahead and put a link in the chat to a resource that Becky is sharing for this workshop. Becky, do you want to just say something about the resource?
Yeah, the resource gives you all the materials that we're recommending in this. There's a free downloadable PDF of the doc cards we'll use, and then links to the other resources and some videos, and some websites that I think will be helpful to you. So everything that you see, you should find a link on there during this webinar.
Great. So let me know if that works. So in a webinar, I'm used to Zoom meetings. I don't do many webinars, but in a webinar, the chat function is disabled, but instead what you can use is the Q&A function. So that question and answer, and I know we are leaving time at the end for Becky to take questions. So if you have a question about what she's presenting, or you're coming to this webinar with a particular student in mind and you want to ask a question about a student, feel free to put those in the Q&A and we will address them towards the end of the session. So it's 10:01. So I'm going to go ahead and let's just do introductions, Becky. What do you think? Should we get started?
That sounds great.
Okay, great. So as I said, my name is Melissa Orkin. I'm the director of a professional development and consulting group called Crafting Minds. And I'm here with Becky Lord. And Becky is she's a math specialist in the Waltham Public Schools, and I'll give you her whole bio in a minute. But Becky has been teaching some professional development courses on math instruction, particularly for students with specific learning disabilities in math. And I saw Becky teach several years ago at her former school district, and I was blown away by her instruction. So I have the great privilege of seeing many, many talented educators teach. I go into lots of school districts across Massachusetts, and I am able to observe, incredible teachers. But when I saw Becky teach math to students and the strategies that she was using, it was something that I had never witnessed before. And I'm so excited that she is able to present this information to you about math facts today, because it's a common challenge that many practitioners face. So let me just give you a little bit of information about Becky. So Becky is an elementary math coach in the Waltham Public Schools and a former dual special education middle school math teacher. So she's got both middle and elementary experience. She has 10 years of experience in specialized math instruction, primarily in teaching substantially separate small group math classes to students with dyscalculia, dyslexia, language-based, and math learning disabilities. And during this time, she also served as a middle school math general education teacher and providing Tier 2 math support and designing and delivering Tier 3 math interventions. So over the past several years, she's provided professional development on dyscalculia, math learning disabilities, and effective math instruction for teachers and districts throughout Massachusetts. So you've been really busy, Becky. And she's providing this information today as a kind of insight into the most effective strategies for really improving students' core conceptual understanding of math. And this is one piece of a larger course that she's offering. So if you find today helpful and you're interested in learning more, we do have a course called Decoding Math that is available as a graduate level course. It can be completed in two different ways. You can either do it through self-guided coursework, or you can complete the self-guided coursework and then attend several live sessions with Becky as well. So we'll talk a little bit more about that at the end. But right now I will just let Becky do her stuff. So go ahead, Becky.
All right, well, thank you so much for that introduction and feedback too. Like most of you, teaching, we're often in the classroom by ourselves, but working really hard. So it's really nice to hear, just that we're helping students and making a positive impact. And I started just a little more, I started right away working with students that were struggling with math, that had enough difficulties that they were being pulled out into a substantially separate program, a small group program. And so, I knew at the beginning with these students that they needed different methods. And that really began this search for me of trying to find methods that were effective with these students for learning math and to really deeply understand it. And so I found a lot, it took me a lot of years and a lot of work, but found a lot of things that are effective. And once I started to see the difference these methods made with students, I just couldn't wait to share them with people. So I love sharing this because I really think you're going to find it so helpful, especially with students who aren't learning math easily. Okay, so let's start with, we're going to just think a little big picture and actually getting into the neuroscience, a little bit of math, which most of us never really learned in grad school or whatever we did for our education background. So what math abilities do you think that we're born with? So it used to be Piaget, who most of us studied probably in human development, had the idea that we were all born as blank slates and that all mathematical knowledge had to be constructed through experience, so that really we're not born with any math understanding. It's all developed through our life experience. And that actually is not what current neuroscience is showing anymore. It's showing that we actually are born with innate abilities to understand number and quantity. And a second question then is, how does our brain learn math? How does math develop in the brain? And the predominant view we've had for a long time is that math is really a function of language. So it's really learned primarily through language and experience, but we tend to teach math in this language heavy way. And through, even if you think of worksheets that are often used in math, there's a lot of decoding, reading, and then the language in order to make sense of and understand math concepts. So if you take a look at this image of the brain, this is what you often see for left versus right brain. So the left hemisphere of our brain is where our language centers are, and that's where reading develops are. And that's more linear thinking. So it's one piece at a time. So think about, when you're reading or you're speaking, it's one word at a time, or, you might see a few words at a time, but it's a linear way of thinking. So we've generally assumed math happens primarily in the left hemisphere of the brain. What's actually being shown in research is that our innate math capacities are actually in the right hemisphere of the brain. The right hemisphere we know much less about. The right hemisphere is really for our visual spatial thinking. It's about seeing quantities. So about the visual, the picture you have in your mind of a quantity. So seeing how much, which really kind of makes sense that math is more about seeing quantities and then picturing that in your mind. So let's take a closer look then at how that actually works. Oops. There we go. Okay, so our left hemisphere here, we just talked about briefly. This is really language reading and more linear thinking. The right hemisphere is where nonlinear and verbal visual spatial thinking happens, which is quite a bit faster actually than linear. Like that idea that a picture is worth 1,000 words. You can take in a lot more through images than you can through language. So let's taking a look at how this works. So I'm going to flash a color here. I want you to look at, but don't try to see the color. My guess is you all saw that that was red. So that is what is considered to be a primary visual capacity, meaning you were born with the ability to see color. Nobody had to teach you how to see color. You just see it and you recognize color. You did, however, have to learn the language. You had to learn the word red and then map that or attach that as a label to that quantity. So you see that and then you had to learn that that's called red. They actually think it's the same thing with numbers and our ability to see quantities. That we were born with an innate, a primary visual capacity to see small quantities and just know what they are. But then we still need to map the language or the word onto what those quantities are. So I'm going to flash some dots here, try to do it quickly, and then just, don't try to count them, but just see if you know what they are. My guess is you were quickly able to see that that was 3. And notice you didn't have time to count them, but you still knew that that was 3. Now let's try a larger quantity. So that one you may or may not have seen, but that was actually 6. And if we put that back up here, likely what your brain did was either break it into maybe you saw 3 and then 3 and quickly figured out that that was 6, or maybe you saw 4 and 2. It's a little bit more difficult. You aren't really able to see all 6 at once, but you're able to break it into 2 pieces and put it together quickly, much faster than you could if you took the time to count them. So this is called an ability called subitizing or subitizing. You can say, either way. So the root of this word is from the Latin subito, which means suddenly. And it's the idea that it means instantly seeing how many. So just seeing it and knowing the number without having to count. And this is actually an ability that young children and even animals have. They can recognize small sets. So there's been research with monkeys and fish and all different animals to show that they actually have the innate capacity to subitize also. And one of the theories is that this is part of the object tracking system in the brain, like how many objects you're able to look at a time. Subitizing is for research is pretty consistent now that we have an innate capacity to subitize up to 4. When you're young, so young children, 2 or 3 years old, might only be up to about 2 or 3, and then it develops to 4 as you get a little older. So your speed of subitizing, your ability does improve as you grow up, but it's an innate capacity that everybody has. So what we can do with the subitizing is extend it to help us figure out larger numbers without having to count. So 2 types of subitizing. The first one is sometimes called perceptual subitizing, and that's just what we think of as our innate subitizing ability. This is being able to recognize a number without using any other mathematical processes. So you just see that 4 and you know it's 4, but then you learn the language 4 and you map that onto that visual representation of 4. Conceptual subitizing is recognizing a number as a composite of parts in a whole. So you might see that 5 there, but perhaps what your mind did was quickly see the 4 and then add the 1 in to know it's 5. And there is research also showing that when subitizing dots are arranged into certain arrangements, it actually extends and improves your ability to quickly subitize. So notice this 5 is more like a dice arrangement. This is considered to be faster for your brain to subitize. It also helps when you have simple objects. That's easier than more complex objects. So these are just simple circles. And also when, the foreground versus the background is very clear. So black dots on white or some strong color or a good amount of contrast between the dots, and that all improve and speed up your ability to subitize. So we're going to use that conceptual subitizing ability to develop actually our basic math facts. So I'm going to show you some dots again, and I want you to quickly determine how many are in each box, and then think about which box was easier to figure out. So from a quick glance, which one did you know more quickly? I would guess probably this one on the right, the 5 dice arrangement. Notice that it's difficult to see 5 in a row and know immediately that it's 5. You probably had to look quickly, maybe break it into 3 and 2 or do a quick count to see it. Let's try another one. Okay, so which one did you immediately know more quickly? My guess is your eye went to the one on the right. Oh, the square, that's 4, whereas the one on the left, you had to think about it. It's just a little bit more difficult to see a 4 in a line like that. And last one, 3. And I'd be curious to hear what you found easier, but likely you might have actually found these very similar. When you're at 3, what the research shows, so if that's what happened for you, then that matches research. When you're at 3, then your eye, it doesn't really make a big difference. You can pretty much see the 3 triangle and the 3 in a row about the same speed. And some of what is coming up too is that we have a natural ability and innate ability for symmetry. We like what's on the right to be the same as on the left. And so I think part of what makes that 3 line work is we can focus on the 1 in the middle and see that there's 1 on either side and take that in quickly. But when you get to more than that, it's a lot harder for your brain to do that. So we talked a little bit about the brain and where these mathematical abilities happen. So where in the brain, this is a part of what's considered to be your innate number system. Whoops, I went back. There we go. It's in what's called the intraparietal sulcus. Now that's definitely a lot of brain vocabulary that I won't, get into right now. You can Google some of it if you're wondering, but it basically means it's in the parietal lobe, which is sort of the back of your brain. And the sulcus is what they call, if you think about the brain has those bumpy appearances, the sulcus is where you have a groove and where it sinks in. So it's just located in one of the grooves of the brain. So the intraparietal sulcus is where your innate mathematical abilities are. So let's take a little closer look at the brain here, and it's mapped out. So if you look at this picture on the right, you'll see here where it's number 3, that right groove, the red groove there is called the right intraparietal sulcus. And on number 2 here, the red groove is the left intraparietal sulcus. So what's interesting is that your innate ability to see quantity and know what it is actually more in that right hemisphere. It's really that right intraparietal sulcus. So this idea again that math is left brain, really our visual capacities are more in the right brain. So if we're teaching math in a way that's really emphasizing language and that, we want to teach the language, but that's not the basis of understanding the math. What happens though over time is that as we learn the symbolic form of number, so think of the written numeral, 3 as a code. It's a symbol that represents a quantity of 3 dots. That symbolic form though develops in the left hemisphere. So as kids learn, as they develop a good conceptual understanding and then develop this understanding of a symbolic form, it actually will activate in the left hemisphere of the brain even more. And so you'll see as you get older, if we were to do fMRIs, the same topic will activate in different parts of the brain depending on your kids' ages and how well they've learned something. So again, the visual, seeing those dots and knowing them is more the right intraparietal sulcus. And then as you learn the symbolic form and get more comfortable working with the symbolic form in written equations, that develops more in the left hemisphere. So we really want those things to work together. There's a phrase in neuroscience of neurons that fire together, wire together. So we want the conceptual, visual side along with the language and the symbolic form to all fire and wire together. So let's take a look at how we can do that a little bit more closely. So what does this mean for math instruction then? Well, first of all, currently, what is the primary strategy for math facts? I would say from a lot of what I've seen, it's counting. We teach students to count all, and then to count on, and then to start from the larger add-in to count on. And that's our primary strategy I see us using in elementary schools to teach students to count. And having worked with middle school and high school students, often those students are still actually counting forward and back in order to add and subtract when they're doing much more complex problems. So what's the problem with counting? Well, first of all, counting requires a lot of cognitive skills. You don't have an innate ability to count. You have to learn that through language. So counting requires language abilities. It requires the ability to sequence and to put things in order. It requires working memory. So your working memory is how many things, how much you can hold in your mind and think about at a time. And so if you're counting, you have to keep track of all the pieces, all the numbers you said, the math problem, and put it all together in your head. So it's a big demand on working memory. It also requires part to whole thinking, which means when you're counting and looking at the individual pieces of, let's say you're counting for 5, and then you have to be able to put those pieces all together to understand that that total quantity is 5. Sometimes kids say that word 5, but they haven't really put together the concept in their mind that there are 5 objects to make up that 5. And it requires also the ability to construct a mental visual. So if math is really about this ability of having to see visuals and have a good picture in your mind of quantity, if we're counting, it doesn't give them that visual to have in their mind very well. And so I like this image here. This is often the manipulatives we see in elementary schools. We've got colored tiles, counters. I'm just going to move this, colored counters, counting bears, counting sticks, cubes. A lot of different kinds of manipulatives that can be used for counting is often what we see. And so what I'm going to do is recommend some different manipulatives instead that are more effective for developing these concepts. Okay, so the 3 tools that I would recommend, and these are all on that resource document we shared with you, is first of all, dot cards, which were developed by Chris Wooden at the Landmark School up in Beverly, Massachusetts. And he has a website, woodenmath.com. The second is cluster cards, which are developed by Mahesh Sharma, who's in Framingham, Massachusetts, and he has a website, mathematicsforall.org, and this is all on the website on that document. And then third is Cuisinart rods, which you've probably heard about, but maybe aren't sure how to use if you haven't used them. And what I'm going to share with you is also things I learned from Mahesh Sharma. So let's get into this more deeply. Okay, so these are the dot cards. from Wooden Math, developed by Chris Wooden. And so what's great about these, if you take a look, notice 1 through 5 is really all those images that you can quickly subitize, that your brain has an innate capacity for. So what I would often do is start with students, and I'll just take the dot cards and I'll tell them, I'm just going to flash them. I want you to quickly tell me how much it is, so what's this? 3. And a great thing to do is, if you think students are counting, just hold it and take it away. Because actually what's happened for a lot of students is we've so taught them that they need to count that sometimes they don't trust themselves. They think they're supposed to count them. I want to encourage them to just know it. Just see, oh, that's 3. And then I might flash, so what's this? 2, 4, 1, and then 5. And often students are able to do 1 through 4 very easily. And some students, if they have a little bit of maybe a weakness with math, 5 can sometimes be more difficult, but then they'll learn it quickly that there's 5 and that 1 in the middle. And notice these cards, they're all a symmetrical arrangement, which really helps your brain as well. And a common question that comes up is, well, what about 10 frames? Well, think about 10 frames. They're really a linear arrangement. It's just not as easy for your brain to picture. Your brain can picture these quite a bit faster, which helps you to internalize math understanding. Our goal is not that students will forever be dependent on concrete materials and written things. We want to use these arrangements because it's what your brain can most easily image and picture on its own, so that we can actually see those manipulatives and not have students needing them all the time. So another thing that I would recommend you do with these is actually, as you hold them up, have students show you the correct number of fingers as you flash them. So as I show this, it would be 3, 2, right? 4, 1, and 5. And there's a couple of reasons for this. One is that, and the main reason really is that research has shown that when you represent numbers on your fingers, it actually activates the same part of the brain where your number sense is. So one of the researchers doing a lot of work on dyscalculia and how we learn math is Brian Butterworth. So he talks about there's actually 3 component abilities that are necessary or helpful for developing math. And it's subitizing, it's actually fine motor abilities, and something called finger nausea, which is your ability to represent in your brain what you saw or how many fingers you have. Like if I have this, that's 3 fingers. And so what's important here is that I'm not having kids count their fingers. I'm teaching them, when you see 3, this is 3. We're not going 1, 2, 3. And it's just the standard finger arrangements. It doesn't need to be anything complicated. And so this is actually strengthening the number sense in their brain when they do that. So when they see 3, say 3, and they're doing this to 3, we're developing all of that and wiring it together. Okay, so what you can do with that also then is have students, what I want them to do is really get a good understanding of all the combinations that make 5. So another activity you can do is take something like, I have these little red discs, and I'll give students a pile and ask them to make that 5 pattern. I'm always curious to see if they can make it without seeing it again, as long as I've already shown it to them. And if they need to see it, I just hold it up again and they show it. So what they can do is, once they've made that 5 pattern, if you're picturing, the 2, 2, and the 1 in the middle, is then I can, take some away and have students, so what did I do? What's missing? Can you put it back? So what you're teaching students to do is to image that 5 in their brain so that they understand when something's missing. And then they can see, oh, well, you took 2 away. I see 3, so you took 2 away, so I can put those 2 back. And we'll do a lot of activities for that. And that's actually how you can introduce addition and subtraction. So if I have 5 and I take 2 away, I can put my arm straight out to the side like a subtraction sign. So that's take away 2. And then when we put them back together, we can actually then, 2 and 3, if I put that together, if I add it together, it makes 5. And it's a great way to start introducing addition and subtraction concepts just with visuals and arm movements. So there's no writing at this point. Once students do start to get more comfortable with a concept, that's when you can bring in the symbols. So the matching or the writing for the symbols.
Becky, that's such a fantastic technique. Would you mind actually just showing that to us again? Maybe just stop sharing your screen for a second so we can just see your video and the video of your face. And can you do it one more time and show us?
Yeah. Okay. And so, right. So I'll just stop sharing so that
we should just see your face. Yeah.
I'll be a little bigger on your screen. Okay. So like I said, what I like to do, and you can do this in different ways. I'll show you. You can take these 5, red discs. If students have them in that 5 arrangement, I just can't really show you something on the table at the same time. And then if I take these two away, I actually put my arms straight out to the side like this, like a takeaway sign. And so what's left? Well, on the other hand, I have the 3 that are left, or on the board. If you had it just on the table, they'll see that there's 3 left. So you can do that. What did I start with? 5. What did I take away? I took away 2. So what's left? 3. So it equals 3. And then we're going to do the inverse. So now what am I starting with? 3. So now we're going to put this back. I'm going to add back the 2 and the 3 together. And then what do I have all together? Now I have 5. And you can do this both with the 5 on the board, doing that, or actually holding it in your hands. And you even could use the dot cards for that. So for example, if you have, the 3 and the 2 here, you could have 5, take away 3 equals 2. So 2, add back the 5 and do this, that you're putting them together equals 5. Or
That's
put it
great.
this way.
So do you also show them the number while you're doing that? Do you show them the actual numeral?
I don't at the beginning, because really the weakness for most students is in their conceptual understanding of number and in these images. So at the beginning, what we're really focusing is on developing the visual representations of the different numbers and the language that goes with it. So mapping the language onto it, so that when I start to introduce the symbols, now it has meaning and it makes sense. So one student, depends on the age of the student. Younger students, they're going to want to do more of this before you bring in the symbols. As students get a little older, they've used the symbols and it's okay to bring them in more quickly. So I might do that first and then have students. So how would I write that? And I like to use a graphic organizer, which I'll show you, something like this. You can see that okay?
Yeah.
Where they would then write, and notice, the circles are for the plus or minus and equal. So prompts them and gives them a structure to know, oh, I need a number in the square and I needed a symbol like an addition or whatever it is in the circles, and just start writing that way. If students are not strong with writing, or you're just getting started, sometimes I'll have number cards out and symbol cards, and I have the numbers are squares and the symbols are circles, so they can actually match it. And that can be an easier thing for some students too.
And so and just one more question, are you doing this, are you working within a certain number family? Like, are you working on all the 3s first, like 3 minus 1, 3 minus 2, 3 minus 3, or are you following a particular progression?
Yeah, good question. So 0 through 5, you can do them all pretty quickly because students have that natural ability to subitize up through 4. But you do also want to go back and make sure you teach the decomposition of every number. And I'll talk about that a little bit more with the cluster cards, how you do that. But then I would go back and, and just be clear that, 2, what can I break 2 is like 1 and 1, or 0 and 2. So those are the 2 combinations that make 2, 0 and 2, or 1 and 1, and that's it, right? 3, we have 1 and 2, 2 and 1, or 3 and 0, because I want students to be able to image, take them away, and put it back.
So what I'm noticing is that you're totally not using the numerals at all. You're not using the actual form of the number. You're really using the dots as a way of supporting the conceptual understanding of the quantity of these numbers. Okay.
Yes, and that's really the part that we tend to be missing. So the symbolic form of number is not innate to the brain. We're not born with neurons that instantly recognize those symbols. That meaning has to be developed. So I think because we tend to teach a lot symbolically in math, students really are actually weak in the conceptual visual side of, and the number, this is really the number sense. And teachers are often saying, how do I help my students have stronger number sense? Well, it's really through using these really effective visuals, developing meaning, and then you do work on the symbols, but I want those symbols to have meaning. So when they see a 4, they understand that it's that 4 dot pattern.
Great. Okay, sorry. Yeah. That was a really good clarification, hopefully for other folks on the call, but also for me. Okay.
Yeah, I think it's all, there's so much great stuff. I'm happy to share all of that. All right. So, so that foundation of teaching 0 through 5 is really the foundation then for 6 through 10, because if you look at these cards, you'll notice 6 through 10 becomes just a complete 5, an exact same dot configuration for the 1, 2, 3, 4, 5 to make the combinations. So after we've worked on 0 through 5, we can start to work on 6 through 10. And so often what I'll do is just switch to, what's this? Well, the only difference in this 5 is it's blue now. So really what this does, and the way Chris Wooden developed this, is that blue represents your left hand. So once you get to 5 or more, you can show the complete 5 on your left hand, and then whatever the red is your right hand. And so when I get to, 6, it's going to be 5 and 1, right? so that you're going to see the decomposition, that it's a 5 and 1 more. And then I might go to, you can go in order and just do 6 and work on that for a while, depending on the age of the students you're working with. I'm tending to working with slightly older students, so I'll show you. I usually get into the bigger numbers quickly. So what is this, right? And notice the 5 and 5, it's really quick and easy to see that that's 10 altogether. And I want kids to know, that's 10 fingers. So we're actually practicing having kids know how many fingers they have too. We know some kids struggle to learn that. So what's this one? Well, notice there's only, what one missing to make it 10, right? So that's that 5 and 4, which is 9. So we'd represent that like this. What's this? 7, so that'd be 5 and 2. And what's this one? This is 8, the 5 and 3. Okay, so there's a couple things that are great about this. I would do the same kinds of activities with these, but one of the things that's great about this is seeing what's missing to make 10. So just like we did what's missing to make 5, now, look at this 8, what's missing? Well, if you see this is a 5 and this is a 3, oh, well, it's just the 2. We already know that. We already know that 3 and 2 makes 5. And so 8 and 2 would make 10. And the same with, what's this? The 6. Okay, so there's only 1 here. So what's missing? Well, it's missing the 4 square. So 6 and 4 makes 10. So you can go through all these and have kids practice what's missing to make 10. And the better they've imaged this in their mind, the more quickly they're able to see what's missing. Oh, well, that's the 7. Oh, I can see 3 are missing. And notice there's no counting needed. It's just that picture, having gotten a good picture and recognizing what's missing. The other great thing about this is that it's really helping kids build this decomposition of 5 and 2 is 7. So they understand 7 is 5 and 2. Often 7 and 8 are where we struggle the most. And so I want to show you how this builds as you get to, I just have another set here where I actually printed 2 sets and put them together. So if I want to work on doubles with students, and I'll start to show you some addition past 10, you get, what is this? 5. So then I'll say, well, double it. 5 and 5 is 10. I might actually stop sharing again so you can actually see these a little bit bigger. So 5 and 5 is 10. And, I was teaching remotely, so I would put these right down on the table under the document camera or whatever works best for how you're teaching. So then how much is this? 1. So double it. Now that's 1 and 1 is 2. So how much is this? Well, notice, this is 6, right? So what if I double it? So what I can do is put it together like this. And notice I already did the 5 and 1. So students have that 5 and 5 is 10 and 1 and 1 is 2. So something that can be helpful is to actually take these and turn it this way. And what you'll see is the 5 and 5 double to make the 10, the 1 and 1 double to make the 2. And so students can see, oh, it's 10 and 2, 10 and 2 is 12. And so these are actually a really effective way to teach the doubles. And again, let's just do one more. So 2 and double it, 4. So what's this? 7. And then double it, and I'll hold that up again and turn it. You can see that the 7 and 7, the 5s make 10, the 2s make 4. Okay. And students can also think about, if you have 7 on your fingers and I double it, well, this 5 and 5 will be 10, this 2 and 2 will make 4, 10 and 4 is 14. And usually what I do actually before doing numbers larger than 10 is to just talk with students about, well, these dot cards only go up through 10. So how could I build the number 11? And usually students are quickly able to figure out that an 11 is going to be a 10 and a 1. So we'll practice building numbers. This is 10 and 1 is 11. So how am I going to build 14? Oh, well, 14, I teach them has to be a 4 and a 10. So 10 and 4. Now I can't tell if I'm reversed. So I would always put the 10 first. I set up this place value concept by always putting the 10 first and then the smaller number to the right of it, so that students get used to building numbers in the order that it's going to match how we write them in the place value system. But notice what's important again here is I'm not having them count to 14. And when students see 14 as a complete 10 and a 4, the number sense they get is much stronger. And it's actually much easier for the brain to understand 14 that way than it is to count 14 individual objects and try to put that together into a whole in your mind. Okay, I think I'm going to show you a couple more other things now with Cuisenaire rods, the cluster cards, unless you have, and I don't know, Melissa, are there any other questions, or do you think that that is a pretty good summary of those?
Yeah, I think that's really helpful. I appreciated the way that you showed how with doubles, you're always holding the cards next to each other. And that's a great technique because I know, especially as we get up into 6 and 6, 7 and 7, 8 and 8, that's always tricky for students, those higher numbers. So one question that came in from Julia is, when initially introducing cards, do the kids count the dots to learn what they are? Do some kids want to count to add? I imagine you need to dissuade them from counting.
So it is a good question. If students if they don't know what it is and they need to count it originally, then that's okay. It's okay to let them count if you need to. Because students have an innate ability to subitize, they often know the 2 and the 3 and usually the 4 without needing to count. But if you feel like they do, that's okay. And then you're going to practice that image. Something I didn't talk about is that one of the things Chris Wooden does also is encourage students to see each one as a shape. So the 4 is a square. And that helps them to see it as a whole. Like if you were showing students shapes, if they said it was a triangle or a square, did they have to count the sides, or were they able to recognize it visually? They're probably able to just recognize a triangle versus a square without counting, because that's an innate ability. And so you're building on that to help them see it as a whole rather than counting.
That's
When
so
you get to
cool.
when it is really, I'll show you a visual too that shows those shapes, because it's a really helpful way. When you get to numbers, let's say like 8, probably I'd rather them, well, can they count on? Can they start at the 5 and then count 6, 7, 8 if they don't know yet that all together is going to make 8?
Okay.
So encourage them if needed to count on instead.
So counting is less encouraged 5 and under, and if necessary, above 5.
Yeah, I think, try to do the subitizing and piece it together, but if students are stuck, it's okay to let them count it. And then you can practice imaging that visual.
Okay.
The other tool I was going to show is these cluster cards, which are from Mahesh Sharma. And I have, so the great thing about these is they're a deck of cards. So you can actually play games, and they extend this to different arrangements. So you actually get not just the 5, and then there's different arrangements for some of the different numbers. Like 8 has the 5 and 3, and it also, or a 6 and 2, and it also has the 4 and 4 kind of traditional arrangement. So on the website, and I put a link on this, there's videos of me teaching all the decomposition of every number from 1 through 10 using these cards. And we do at the beginning teach students, let them count them if they need to, and really go piece by piece to help them to image that card in their mind. Because eventually I want them to, know that that's 9, but they have to image that. They have to break it apart into pieces and see, oh, there's 4 in this row and 4 here and 1 in the middle. Or I can see that as a 5 at the top and a 4 at the bottom, and know that 5 and 4 makes 9, 8 and 1. There's different ways to do it. So this isn't,
I mean, this is a real philosophical shift, I would imagine, for many educators, right? Moving away from, so much reliance on numerals and really using your instructional time to ensure that students have this conceptual understanding. And the reason that I hear you saying that you do that is because the core weakness for many students is with the conceptual piece, not with that paired association between numeral and quantity, right? It's the conceptual,
yes,
what
and
does quantity represent?
right, and to pair it, you need to have a strong conceptual understanding. And I think it's just because we haven't had a good understanding of how math learning developed. We thought it was through language. We've done a lot of writing and talking and writing numerals, but we haven't really emphasized this visual. And not only just visuals, we are using visuals more and more in math now, but the best visuals that actually work the best for your brain. So these arrangements of the 5s rather than 5 in a row makes a big difference. So yes, it's understanding that this is actually the heart of how our brains understand math. And I think that this is why so many students are struggling to learn math, is because we're teaching them in a way that's actually misaligned with how the brain really understands number. And the more you can bring it into alignment with how the brain actually understands number, you're actually going to find students learn much more quickly and easily. And math is fun. It's not such a struggle like it often is.
Awesome. So it's 10:37. Do you want to show us something else, and then we'll see if there are any more questions to take?
That sounds great. Okay. So just to quickly show you with the dot cards. So these are the shapes, so it's 1 is a dot, 2 is a line, 3 is a triangle, 4 is a square, and 5 is an X. And so you can have students see it as a shape and help them. Chris Wooden does more with this. So on woodenmath.com is a great resource for more activities around this if you're curious to check that out. And then I also want to show you this, which I think is really cool because it is actually taking the symbols and mapping them onto the dot configurations. Because quite often what happens for students is those numerals don't really have meaning. You might learn that it's the word 6, but students have difficulty visualizing 6 dots. And so you'll notice the 6, has this arrangement of the 6 going right over it and the 7. And so these ways of looping it together can help students see, because what I've gone to the point is noticing now that I've gotten used to this, I see this and it's, oh, there's the straight line at the top of the 7, right? And then it goes through like that. And you start to be able to visualize it. Here's the 8. Well, this is the circle top of the 8, and then this is the bottom. And so it helps you to see this 8 and actually connect it to what the symbol of 8 is.
Yeah, that's super cool. Yeah, so thoughtful.
Yeah. I've had a student say that looks like, the infinity sign. It's like, oh, that basically is the 8, right? And so they saw that configuration on their own too before I showed them this, which was great. Okay, and so then the cluster cards, just a little bit more about that. These were developed by Mahesh Sharma. And you can see that these really can be used in a lot of ways. So I use them to develop all the combinations for every number 1 through 10. And those are the videos that are available at that link. So I won't take time now to go through that. You can watch those videos. I made those videos also at the beginning of the remote schooling when we first shut down. So I made them like I'm teaching kids, which means you are welcome to share them to teach kids or use them in lessons and have kids use it as a way to practice and to learn these combinations. So we developed that decomposition. It also helps us develop efficient strategies. So rather than counting on, we're seeing these and we're seeing what's missing to make 10 or how to combine them that way. And the other great thing is because it's a deck of cards, you can actually play games and help students practice. So instead of go fish, you can make, go make 10 or go make 9, where kids are trying to match those combinations that make 10 or make 9. And again, the great thing is these do not have a written numeral on them. So students have to subitize or figure it out. And you're going to encourage them to see it and know it, not count the individual dots over time. You also can play number war. So, addition or subtraction, have kids each flip 2 cards. They have to add it together, or they have to subtract them. Whoever has the larger result wins. You can have them multiply the 2 cards that they flip over. If you're a teacher of older students, you actually can use them for integers, where usually the black represents positive and red is negative. So you're combining integers and using these same strategies for integers. So I won't go into that today, but it's nice to know that you can actually extend this to higher grade levels as well. Okay, so the last thing I want to show you, I know we just have a couple more minutes here, is just a little bit about Cuisinart rods. So these are the other tool that I highly recommend. And I know if you're like me at the beginning, I was like, I do not like these Cuisinart rods, because how are you supposed to know how much each one is? Each rod does not have any lines on it, so it's not instantly clear how much each quantity is. And so what I've learned about it is that that's actually what makes Cuisinart rods so effective. It helps, because you can't just count, it helps students move away from counting individual pieces and get into that idea of chunking numbers. It also helps to develop this concept of number as a length, so a continuous understanding of number versus discrete objects. And what I often have been doing is holding up a dot to help students practice when they're first learning the Cuisinart rods, is to hold up a dot card like this is 4, and then have students find the matching Cuisinart rod. And so that can be a great way to have them practice and connect that, this is a 4 dots, and this is a 4 also as a 4 Cuisinart rod. Just connect those like different representations of quantity. And the great thing about these two is you really can build any multi-digit math fact. Cuisinart rods are the same size as base 10 blocks. So they're 10, a 10 rod is 10 centimeters. You actually can use them to measure with because they're in centimeters, and you can use them right along with your base 10 blocks and your 100 blocks. So I am going to attempt to switch my camera so I can show you these a little bit more. Let me let's hope this works. Okay, there we go. Okay, great. So the first thing that I would have students do if you're starting with Cuisinart rods is just to let them play with the rods. So they're actually, they're colorful blocks. Kids love to just play with them, and that gives them experience. I'm going to slide this over just a little bit. It gives them experience in getting to know what they are. Then I would have them take out one of each color and have them build this ladder, staircase, and actually figure out how much each one is, and they can touch them and count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can start to develop which number is which like that. I also will have students take out, for example, a 4 rod, and we'll actually take 4 ones and put them end to end like this. I'm just going to put 1 there. I don't know if is that too small, or can you see it a little bit? Hopefully it's okay. And actually put 4 ones there so they determine that that's 4. But we can figure out different combinations and ways to make 4. So there's more you can do with it. I'm just going to move quickly so I can show you just a couple other things with these. Have kids play a game. You can build bigger numbers. So, if you take a 10 and a 4, that's how you can build a 14, right? So if I'm adding 10, let's say I'm starting at 4 and I want to count on by 10. So 10 and 4 is 14. Another 10 and 4 is 24. Another 10 and 4 is 34. So you can build different numbers this way. And that's a great strategy to use. Then I like to have students make all the combinations. So this is the combinations for 10. And if you even look at this, I could say, well, if this is a 9, 9 and what makes 10? 9 and 1, and put that right there. And students can see that the 9 and 1 would make 10. And the same, we could do 8 and 2, 7 and 3. So students, the great thing is they can work on this on their own because it's going to give them that feedback to see whether or not it's correct. If I put a 3 here, well, look, that's actually not the correct length. You can see it. So students can do it on their own. You don't have to be standing there the whole time telling them if they're right or wrong. Like sometimes that happens in math. They're going to be able to figure out what length it is. So if a student, for example, wants to know, they're working on 3 plus 4 and they're not sure if they have the right answer. Well, you can just say, well, take out a 3 and a 4 rod. Well, here's a 3, here's a 4 rod, put it end to end. So what is it? You've got to figure out which rod is the correct length. So let's say I put an 8 here. Oh, that's not right. If I put a 7 here, I'll look at that. That's correct. So 3 plus 4 equals 7. And so it gives students the chance to use visual tools that these are very efficient. Notice I'm not often what drives teachers a little crazy. You're counting out all these individual 1 pieces. This is much faster. Students are going to be able to put that together, see that that's 7. And then you can do, well, 7 take away 3 is 4, right? Or 7 take away 4 is 3. And build both your addition and subtraction facts that way. Okay, so getting into, just to show you quickly how you would do a larger number. Well, what if I have 8 plus 5? Well, students will take out an 8 rod and a 5 rod, put it end to end. Okay, and then the question I usually have them ask is, they'll say, is it more than 10? Yes, it is. So anytime it's 10 or more, we can tell by, visually. If not, they can always just try it. We're going to take out a 10 rod. Okay, well, 8 and what makes 10? So this is where those combinations are so important. Well, we already know 8 and 2 makes 10. So if I have a 2 here, and I could even take a 2 and put it there to help students see. So 2 and what would make the 5? 2 and 3. Okay, so I can actually move this right here and have students figure out. So 8 plus 5 is 10 and 3, which is 13. Because I would have already taught them that 10 and 3 are 13. All right, so that's just a really quick way to show you how you can take this up to larger numbers and use those strategies. I wanted to show you one multiplication fact before we wrap up too. Do you have any questions, Melissa, on this part of the addition though with Cuisinart rods? I know this is just a really quick exposure to these.
Yeah, so it sounds like, well, Isha has a question. She said, for questions greater than 10, what do we do when they cannot answer it automatically if they resort to counting on? For example, when teaching doubles, the student can figure out 5 and 5 and 2 and 2, but it's not automatic of putting 10 and 4 together. So at that point, would you switch to Cuisinart rods from the cluster cards?
Yeah, anytime a student is struggling, I go back and with the visuals or the tools. So, the Cuisinart rods are definitely a little bit more advanced than the dot cards. And so the dot cards and the cluster cards are a better place to start. But students can start working with these as well pretty quickly, and then they'll start to learn them and get that information. So if a student doesn't know something, I just say, well, build it. If they don't know what 10 and 4 is, then we're going to build a 10 and 4. And I might need to teach them then that 14 means a 10 and a 4, that teen is a 10. And then that means we need to practice it if they don't know what that is. If they don't know what 7 and 7 are, then I'm probably going to use the dot cards because I think that that's the clearest. To see that the 5 and 5 makes 10, the 2 and 2 makes 4. So now 10 and 4 is 14. There's a lot of embedded skills in math. And this is actually, I think, where we often struggle too, is that whenever you're teaching a concept, think of all the pre-skills. What are all the embedded skills? So students need to understand the teen numbers, that it's 10 and a number. They need to understand how to double 5 and how to double 2 before they're going to be able to understand that 7 and 7 makes 14.
Right.
So you work on those things first, or if they get stuck, you go back to whatever piece they're getting stuck on, you go back to that.
Right. So if you're an educator, let's say, and you've been working with a student and you've been using the flashcard approach, but you feel like it's just not making kind of the impact that you want, what you're suggesting is really think about what are the underlying skills and try to use these kind of this shift in approach in some of these different manipulatives, whether they're the dot or cluster cards or the Cuisenaire rods, to build up the conceptual understanding at the foundational level.
Yes, exactly. And these visuals, the great thing, they're really going to help kids develop efficient strategies. Otherwise, kids are counting. But when you see these, you know, and you could probably see the dot cards, visually, it's so much easier to see, oh, 8, 2 are missing to make 10. And so you build those really strong strategies and that mental visual kids get. And then when you get to the math facts, you're not trying to explain it to them. Sometimes I feel like with kids, we're trying to explain to them everything they're not understanding, and they can't absorb or make sense of all that language. The visual is so much more effective. But then you get to the point, you know, I was working with a student and then we'd fade the manipulatives and be like, okay, double 7. So can you picture 7 in your mind as that 5 and 2? Well, you know, now double it. So she would actually picture it in her mind and double it to get the 14. So when they see the written number 7, we wanted to activate the picture in their mind and then they work with that.
Got it. And the Cuisenaire rods are so accessible too. And they're not intimidating, I think, to most students.
Yeah, the kids really love the colored blocks, and there's really so much you can do with them. I'll just show you because I know we're getting to the end, and I'm sure some people would love to see some multiplication. So I'll just show you a multiplication problem quickly. So this is 5 times 6. So what I do is teach students to build the number both ways. I'm actually going to model, because it's just going to show us some better strategies, 4 times 6. So I will write this here. Usually by this point, you know, students have developed some more understanding of the written numerals. So if I have 4 times 6, okay, so that's this. So is that backwards or is that okay?
Look, it looks good.
Okay, good. All right, so I have a 4. So I could think of 4 times 6 as 4 repeatedly added 6 times. So that's the first meaning of multiplication. So this is a 4 repeatedly added 6 times. I also could think of it as 4 groups of 6. So that's actually modeling it like this, where I have 6 4 times. So 4 groups of 6. So 4 times 6, you know, is the same as 6 times 4. And so these two models also help to develop that concept of commutative property. So I've got the meanings of multiplication here. I've got commutative property representing that this and this are the exact same amount. And the way I can show that to students is actually lifting this and putting it right on top and having them see that it actually works out to be the exact same size rectangle. And that's a helpful way for them to understand commutative property, that it really is the same thing. Also notice I put these into a rectangle, which means we're really using the area model, the area of a rectangle. So what I do is teach students to touch the sides and read it. So this is 4 times 6 equals, well, area is the inside. It's the number of squares inside a shape. And so recognizing that that total number of squares on the inside would be the area. And so when we're working on strategy, so I would have a student build it, understand it enough to build it, and then look at this. Well, what if I don't know 4 times 6? Well, what do I know? Well, maybe I know by the time I'm doing 4 times 6, I should have already learned 4 times 5. So I can say, oh, well, I know that I can break these apart. I know that 4 times 5 is 20. So look, oh, it's only another 4. So it's 24. And that's a much more efficient and conceptual understanding rather than, so skip counting in a sense is like the multiplication version of counting. So it's fine for students to learn to count and skip count. I'm not saying it's not, but it's not an efficient way for them to learn facts. And so I want them instead to build them and then decompose it. So this is, you know, 20 and another 4 is 24. Well, this one would be 6 times 4. Well, maybe if I don't know that, well, do I know 6 times 2? Well, that's really just doubling 6, right? So 6 times 2 is 12. Look, this is also 12. So now 12 and 12 is 24. And I might have needed to teach students to build 12 ahead of time. Sometimes I'll do this. Let's build the number 12. And then I'll say, well, now let's double it. So we're going to build another 12. And then to double it, I'm actually just going to combine these. So look, the 2 10s makes 20, 2 and 2 makes 4. So that when I go to doubling this, they already have this in their mind. Or if they're stuck, I'll do this on the side to help them understand that doubling, how that works out.
Yeah. Or you could drop down, if they're really struggling, you could drop down into the dot or cluster cards, right? To make sure that
Yeah. And it depends on where they're getting stuck. So this is where, you know, listening to students and really paying attention to which parts they're understanding, which parts they're not, helps you figure out what you need to do to remediate or where you need to go back and build understanding so that they have it better. It's so different for students. what I want them to do then is get in the habit of reading this as 6 times 4 is 24, or I can read it as the inverse. 24 divided by 6 is 4, or 24 divided by 4 is 6. So just in this one lesson, we are doing the meanings of multiplication, area model, commutative property. When we break it apart and put it together, it's distributive property, and we're reading it as multiplication and division. So you're covering a lot of really great concepts and building the conceptual understanding. And then of course, we would keep working with this to get to fluency and then use other practice. As students are understanding, they're developing these good strategies, then we're going to start to fade the manipulatives, ask them to picture it in their minds, and then, you know, work on getting to fluency.
Great. And just a question, how do you store your Cuisinart rods? Do you have little boxes where you store rods and the 5 rods?
Such a common question. I got these. This is a big bin, you know. So this is 3 sets all together. Maybe I'll stop sharing for a minute so that it's a little bit bigger. I'll just go back to.
Okay.
I'll actually switch the camera back to this. There we go. So I have a bin. You can probably see it a little bit better here. You know, I got these at Target. I think they're a little less than $5 a bin. You can find some cheaper ones. It depends. I think I got these on sale, fortunately, for like $2. I prefer that. I just get the Cuisinart rods in a bag because I like to combine a couple sets. And so I'd rather, and the great thing is they have these, you know, latches on the side with a lid, and it's easy for kids to get them in and out. So I found that's effective. You know, when students are able to share materials, you can put them out on the table, and it doesn't matter if they get mixed up, they pull from different bins, and then we just close them up at the end.
Great. Okay. So I do want to give people a chance to ask questions. I know that there is one question in the chat, but if other folks who are on here have questions, please feel free to put them in the chat. And while we're doing that, maybe we should talk a little bit more about because this was really cool and amazing information, but it's fast. It went fast, and it's hard to have, you know, a real kind of solid approach within an hour webinar. So we did create a course, and Becky created this course because there was so much interest. Math has been kind of a long neglected area within learning disabilities, and there was so much interest among special educators in like, what are the strategies I should be using? So we have this course that's a graduate level course. It's called Decoding Math. We had a version of it in the spring, but even the version in the spring was only 15 hours. So we've doubled the amount of time so that it can really cover more comprehensive content. Do we want to go through the modules really quickly?
Yeah, yes. So like Melissa's saying, you know, there's so much need, there's so much things in math we want to understand better. And so this course is all the work I've done, everything I've learned that I found so helpful that I just am happy to be sharing out. So the first module, there's 10 modules in the course. There's 30 hours of online, completely self-guided content. So it's videos and resources and things to watch. The first module is on the neuroscience of math and dyscalculia. So you got a little taste of that today. The second is on other cognitive factors like working memory and language abilities that affect math, as well as a little bit of assessments and qualifying for a specific learning disability in math. The third is a foundational ideas of instructional methodology that's effective for math, as well as a number concept, and that's really getting into these dot cards and the work from Wood in Math. The fourth one is on decomposition and recomposition of number, and this particularly gets into Mahesh Sharma's work and with the cluster cards and learning how to introduce Cuisinart rods. The fifth module is on addition and subtraction, primarily with Cuisinart rods, some dot cards as well, and I'm building that up to multi-digit and developing fluency. Next is multiplication division. You got a taste of that again. So understanding how to teach both multiplication division with Cuisinart rods, and then work on fluency, and then generalizing it to multi-digit operations. Then we look at research-based math instruction, and specifically look a lot at teaching word problems. So this gets into getting into what does the research tell us? What do we know about math instruction and what's effective? So we take a deeper dive into the research and find out what methods have been proven to be effective, and then areas where we're still learning more. Next after that, module 8 is getting to planning targeted instruction, to really setting your goal, your learning goals, and then thinking about what's effective to help students learn, about providing interventions and ways to work with students that are struggling to learn, just different ways that are effective. And then also looking at the math components of IEPs and just language you can use to write goals and accommodations in different parts of the IEP. Then the module 9 is on fractions, decimals, and place value, which is another big question area. So we use fraction strips to develop all the fraction concepts and do all 4 operations with fractions, as well as place value and decimals. And then the last module is a deeper dive into math assessment. So this is looking more deeply at different assessments, and the assessment process is both assessments that are not for special education, and also ones for a student who might be qualifying for a specific learning disability.
Great. Yeah, so it's really comprehensive. So you can either do it just completely self-guided for 30 PDPs, or you can complete the self-guided work plus 15 hours of live workshops that take place on Tuesday nights, beginning in October. And they go through December. And the enrollment deadline for the 45 PDPs is September 20th. If you want to do the completely self-guided one for 30 PDPs, the enrollment is rolling and you can enroll at any time. It just needs to be completed by June 1st. The course enrollment is just on the Crafting Minds website, and I'll go ahead and put that website address right at the bottom here. And there are the dates. And so let's go back to the question. Let's see. So Joyce asked, since you just showed the numerals imposed on the dots, what's your opinion of touch math?
That's another common question. You know, the thing that is not great about touch math, right, is that it's really teaching kids to count the individual dots. And I would think of it almost as, yes, it can be effective but it's almost like a short-sighted effective thing. The problem is if students learn touch math, I've had students who are in middle school and they're doing a multi-digit, long division problem, and they get to 8 minus 7, and they start at 8 and they count backwards 7 times to get to 1, because those are the strategies they learn. And you can see how taxing that is on their working memory. Your working memory capacity is only about 4 or 5 things at a time. And so that's taking all their working memory. And so while it might help them to effectively add and subtract and count when they're young, it's not setting them up to be successful in math when they're older. So many students are still counting, even students who don't have learning disabilities, because that's what they learn. And so your brain has to shift all its effort to just doing that one math fact. Often if I say to a student, well, if you had 8 cookies and we ate 7 of them, how many are left? They can say, oh, there's 1, because that makes sense. But they get so buried into those strategies that they stop thinking bigger picture conceptually. So I do think the idea, though, like touch math, of the dots overlaid, so they see those, like on the 4 dots, and they see the 4 there, is a great way to connect it. But it's seeing the 4 all at once. It's not counting the individual dots.
Yeah. So it sounds like you feel like it doesn't go far enough for some students in developing their conceptual understanding. They're still reliant on.
Yeah, and that's really been the strategy. I think in general, we've had a view that students who struggle must need to learn to do a lot of counting, because that's the only way to get there. And it's really just not. And I'll tell you from both Mahesh Sharma, Chris Wooden, anyone I've worked with that's working successfully with students with significant learning disabilities, it's not counting. It's teaching them to see these groups. And I've worked with students in middle school who had not learned any of their facts. And once we switched to these methods, they started learning them so much faster. And they had 6 years of instruction in special education, a lot of them and they still weren't getting it. So it really is so much more effective for the brain. And it's just easier. Brain has that natural ability. And so you're not asking the brain to do all this heavy cognitive effort of counting and sequencing and working memory just to count something.
Yeah. Awesome. All right. Well, it looks like we've answered all the questions. So I just want to thank Becky for taking the time to present this really insightful and impactful information today, and also to all of you for joining us on this late August morning. We really appreciate your time and your energy, and we're happy to share additional information if you have any questions. I accidentally typed the wrong website address, so I've corrected it. And Becky, I don't know if you want to share your email address in case anybody wants to get in touch with you.
Yeah, my email is becky@lordmath.com. That website, gives some basic information. So it's on that website also. So it's pretty simple. I think I had it at the beginning. I don't have it written out right here, but you want me to just stick that in the chat?
I put it in the chat, so everyone should
Great.
have access for that. And we are going to post this recording if you want to watch it again with the link to the resource page, or if you want to share it with colleagues as well. So thanks, everyone. Thanks for joining us. Have a great day.
Thank you. Good luck.
Oh, there were a couple last minute questions. Oh, no. Sandra's saying, how do I get the visual cluster cards? So Sandra, you'll see the link on the resource page that we linked in the chat. So if you go to the resource for the workshop, it's a Google Doc, and it has links to where you can buy either cluster cards from Mahesh Sharma or the dot cards from Christopher Wooden. All right. Bye, everyone. Take care.